So, thank you for this invitation. It's been long overdue. Senia tried to invite me many times, but finally we make it. And so I'm very, very happy to be talking to this audience. So this will be about combinatorics, probability, and statistical physics. And what I want to discuss is some recent extension of the results of the 6-vertex model to a very simple other model, which is called 20-vertex model, and which is just the same, basically, but on a triangular lattice rather than on the square lattice. Okay. So, but before, of course, I do this new model, I will start with recalling a few things on the 6-vertex model, and there's a lot to say, so I'll try to be brief and only extract the things that are important. So one important thing in combinatorics now is this object called alternating sign matrices, which are just another way of looking at the configuration of this 6-vertex model in certain very specific boundary conditions, which I will describe. Okay. And because of the integrability of the model, a lot of things have been able to be said on the alternating sign matrices. And recently, there was even some mathematical theorems about the limit shape of very large alternating sign matrices. So we're going to address all this on this triangular lattice now. Okay, so the second part is just go over to the triangular ice model. It's called ice because of historical reasons. And after defining the boundary conditions, I will show you that the natural object that plays the role of alternating sign matrices in this new model is actually alternating phase matrices, which I will define. And then we'll change completely to some other combinatorial problem, which has to do with domino tilings. And domino tilings are very nice when they are done of domains on the square lattice that have very specific shapes. So there's this guy that I call the holy Aztec square, which for people who know already looks like an Aztec diamond, but with a little bit of defects. And holy just means there's a hole in it, and nothing religious here. Okay, then I'll show you that actually this completely different model actually shares the same partition function with the alternating phase matrices. It's a very remarkable fact, which can be proved, but there is no good understanding of it, just like there is still no good understanding of some relations between alternating sign matrices and other combinatorial objects, like tilings. Then I'll give you more of these combinatorial conjectures. And then I'll show you, well, first I'll show you the proof, of course, and then more of these. And then we'll go over to limit shapes. Okay, so that's the program. And I just want to emphasize that if you want to really reduce this to its basics, it's just a story of 3 sequences. Okay, so 1, 3, 23, 4, 20, 433, etc. 1, 3, 29, 901, and 1, 4, 60, 3, 3, 2, 8. All right. So maybe you already know some of these sequences, but somehow the whole thing revolves around these. Okay, so let me start with recalling things about the square case, right? So why is it called ice model? It's just because it was invented to describe ice in 2 dimensions. So you imagine that the oxygen ions are on the vertices of a square lattice, and then hydrogens arrange themselves on the edges to be in such a way that 2 are close to an oxygen and 2 are far, right? So at each vertex, 2 are close, 2 are far. So you can code that with, for instance, dipolar momenta, and then you can replace this with a configuration of arrows, okay? And now the rule, which was electric neutrality, basically, is that there are as many incoming as outgoing arrows at each vertex. At each vertex, you have 2 entering, 1, 2, and 2 outgoing. All right, so that gives rise to 6 possibilities, right? 4 choose 2. So that's why it's called the 6-vertex model. Now, to that, we are going to add up boundary conditions. So we are looking at a specific case where we're on a square of the square lattice, which is an n by n grid, okay? And on top of that, we're imposing that all the arrows enter horizontally, so from the right or from the left, and come out vertically on top and on bottom, okay? So these are called domain wall boundary conditions, and they were considered a long time ago. The interest of these boundary conditions is that they force domain wall. A domain wall is just a surface along which the arrows are reversed, okay? So you force reversal of arrows just by the boundary conditions, okay? So now bijections, there's very simple bijections. You can rephrase the system in different terms, okay? What happens here is that I have on the first line the arrow configurations, the 6 of them, right? So standardly, one usually puts bolts and weights which don't care about the global orientation. So there's a weight A for the 2 first, the B for the next 2, and C for the next 2, okay? So these are these 3 weights. Okay, so the second way of looking at the configuration is as follows. You consider that these orientations are the basic orientation, so to the right and to the bottom, okay? And whenever in your configuration arrows agree with this, you draw a red line, okay? So of course, this guy agrees with itself, so it's all red, but this guy doesn't agree with anybody, right? Because it's opposite, so it's not painted. And then here the horizontal agree, but not the vertical. So you only draw an horizontal line, okay? So now you can see that I can view the configurations as configurations of lines. And pay attention here, what I have done instead of putting a cross is to detach the top and the bottom part so that they can be part of 2 different paths. But those 2 paths have a kissing point, an osculating point, right? So that's why it's called osculating paths. All right, so view this path as going, say, from northwest to southeast, okay? So from here to there.
Буду до конца недели в Москве. Я на конференцию еду завтра вечером.
This is a question in Russian or a comment?
Oh, sorry.
No, just somebody forget to switch on his phone.
Oh, okay, that's fine. So are we okay so far? The sound is good?
Yes, it's okay. Go ahead.
Right. So on the third line, I decide to completely change the point of view and look at vertices with their properties. So you see these vertices here have the property that they transmit integrally the arrow along the same line as it enters. So here an arrow enters on the left and it exits on the right. So it's transmitted, right? So that's the case for these 4 guys, but the last 2, of course, are reflecting vertices, right? And they reflect in two manners, because here you enter horizontally and exit vertically, and here vice versa. So here is the bijection. You put zeros whenever you see a transmitter vertex instead of a vertex, and you put +1 or -1, depending on the type of reflector vertex you have, okay? And that gives you an alternating sign matrix. So alternating sign matrix is just a notion of zeros, and in which there are 1s and -1s that float, okay? And now along each row and column of my n by n matrix, I see a succession of 1s and -1s, right? So I start to see a 1, then a -1, then a 1, then a -1. And of course, you see an odd number of things because each time you see a reflector vertex, your arrow orientation is reflected, right? And because of a boundary condition, there's an odd number of reflections, right? Because at the end, there is one reflection globally. All right, so these conditions on the numbers of reflections are exactly the conditions that determine the alternating sign matrices. All right, so that's all I wanted to say. So let me summarize. So 6 vertex, the arrows, the osculating paths, the alternating sign matrices. I took the same configuration to show you the bijection. Okay. All right. So just a word on the world of alternating sign matrices or 6 vertex at the ice point. there's a lot of combinatorics that's been done around this recently, on top of all the physics that was done before. And so one particular point is the enumeration of alternating sign matrices of size n by n, right? And it's given by this nice formula. And well, all these people contributed, I mean, especially Korepin and Izergin, who did the heavy lifting, and then other people came after and used their results. Okay. Anyway, there are other combinatorial objects, and I quote only two of them on the right because they are too important. And actually, I ask you to really look at this one. So this one is called DPP, descending plane partitions. So these are just rhombus tiling. So you can see there are three types of rhombi, right, which are tiling an hexagon, but this hexagon has edges n, n plus 2, n, n plus 2, n, n plus 2. So it's slightly irregular, but it has a hole in the middle. So this thing here is a hole. All right. And on top of that, you're asking the following thing. You are asking that the configurations be invariant under rotation of 2 pi over 3. Okay. So basically, this is a fundamental domain, and that's all you have to look at if you want to count those configurations. And the number is again given by this. Okay, so there was a long-lasting conjecture of these numbers being the same and refinements, etc. And it was settled finally. And there's also the totally symmetric self-complementary plane partitions, in which you have just the tilings, rhombus tilings of an hexagon with all possible symmetries, meaning that in the end, there's only 1/12 of the hexagon, which is your fundamental domain under all these symmetries. Okay, and so again, these objects are counted by the same number. All right, but just remember this one, and that will be enough. Okay, so let's go now to triangularize. So what's new? The new thing, well, first of all, I can't draw triangular lattices, so I draw them on the square lattice. So I do this instead, but it's equivalent, okay? So now at each vertex, you have 6 adjacent edges, right? So we generalize the ice rule. We are going to put arrows on each edge. And now, of course, at each vertex, we will demand that there are 3 incoming and 3 outgoing arrows, okay? So the number of choices now is not 4 choose 2, but 6 choose 3, and it's 20. And that's why it's a 20 vertex model. This was studied especially by Kelland and under the direction of Baxter. And so it's Kelland's thesis in which he established the integrable weights for the 20 vertex model. Okay, so here are the configurations, right? Of local configurations, the 20 vertices. And maybe I need to zoom a little bit. So I'm doing the same thing as I did with 6 vertex, right? I choose these as the base orientations, which is still northwest to southeast, basically, and left to right, and up, top to bottom. And now I will paint in red the arrows that agree with this orientation. And notice here that everybody agrees, but I'm splitting this into actually 3 paths, right? So there's now a place for having double osculation, right? Or French ménage à trois, whichever you like best. So these are called osculating Schroeder paths. So why? Because they have 3 types of steps now: horizontal, vertical, and diagonal, right? So that's called a large Schroeder path usually. And on top of that, they're osculating because I'm allowing 2 paths to kiss at the vertex, or even 3 paths to kiss. All right. So in terms of paths, that's what this is. Now let's go over the boundary conditions. So we want to mimic in certain ways the same thing as what was the domain wall for the 6 vertex. So the natural thing is to have everybody entering horizontally and everybody going out vertically. But there's a little problem, which is the corner here and here, right? Is the corner part of the top or part of the left, right? Or here, is the corner part of the right or part of the bottom? So here I have made the choice that this corner is part of the left and this one part of the bottom, but here I have made the opposite choice. So I have two choices. I call them domain wall boundary condition 1 and 2. But if you think a little bit, you can rotate the picture by 180 degrees, right, half turn, and then you're going to map one to the other. So they're the same, actually. They're the same, but looked at in different ways, okay? So these are like the two same. Now this one is different. This one is really emulating the 6 vertex domain wall boundary condition. But now you can see that all the diagonals enter on the south and east and exit on the north and west. Okay, so we've changed the rules a little bit. And in terms of paths, you see that here there are many paths, right? Because everybody is occupied here and goes to everybody down there. Whereas here, only half of the people are occupied and only half are occupied. So there's less paths, so more entropy. So probably the numbers are bigger. And indeed, if you count the numbers, domain wall boundary condition 1, 2, for n equals 1, 2, 3, etc., you get those numbers. And for 1, 2, 3 in the other, you get those numbers. So that's my two first sequences. Okay, so we want to study these guys. All right, so here, just to illustrate the 23 here, right? We have 23 configurations for the 20 vertex model with domain wall boundary conditions 1 on a 3x3 square. Okay. So now let me introduce these alternating phase matrices. So it's just a bijection, a bijective reformulation of the configurations. So you remember we had, so we have arrows that occupy horizontal, vertical, or diagonal edges, okay? Now, if you look at any given direction, which is horizontal, vertical, or diagonal, right, along that direction, well, certain vertices are going to be transmitting, and some vertices are going to be reflecting. So in fact, you have a property now, which is a triple of either transmitting or reflecting at each vertex, right? Depending on which direction you look at, okay? So again, we're going to attach 0 whenever it transmits and a 1 or minus 1 whenever it reflects, okay? But now we, instead of needing just one number at each vertex, we need a triple, right? Because we have these 3 directions. So it's a triple HVD, which are just elements of 0 and plus or minus 1, right? So three elements of 0 plus or minus 1. But now, of course, there's this extra condition that the sum of all the elements should be 0, right? It's the ICE rule. The fact that there are 3 entering and 3 outgoing, you just count and you see that it just means that the sum is 0. Okay? So here is an example, right? I look at this vertex right here. Okay, so horizontally it transmits, I put a 0. Vertically, it reflects in a certain way, which associates to 1. And diagonally, it reflects in the other way, which associates to minus 1. Therefore, my triple is 0, 1, minus 1 attached to this vertex. Okay, so now I have a matrix of triples of integers 0, plus or minus 1. And the remark here is that I can code that with 6 roots of unity and 0. It's very simple. These are just the, if you want, the roots of SL2 of SL3, right? It's one way of looking at it. So you can attach a 6 root of unity to each of those 6 points here, which I call 1 minus 1 minus omega, omega minus omega squared. And all the rest, which are fully transmitting vertices, they have a triple of 0, so I put just 0. Okay, so I fill my matrices with 0 and 6 roots of unity with certain alternation rules, which are just inherited from this fact that when you go along a direction, you have an either odd or even number of reflections when you go from one end to a lattice to the other end. Okay, so here is an example, right, of type 1, type 2, type 3, right, depending on which boundary conditions you're looking at. And this is exactly the matrix that codes this configuration, okay? All right. So there is a very simple fact here, which is that all the alternating sign matrices are particular cases of alternating phase matrices. So here is how you prove this. You take your favorite alternating sign matrix, right? Draw its configuration, either in arrows or in paths. And then on top of that, so you draw it, and now you add up diagonal lines, okay, on top of that. And those diagonal lines, you're going to either occupy them entirely or keep them completely empty, depending on the boundary conditions, right? So here the boundary condition is empty, so you just keep them empty all along. And here it's occupied, so you're going to keep them occupied all along. So you can this way just transform immediately your alternating sign matrix into an APM. Okay? Any question about this? All right. So let's move to something completely different, which is the story of domino tiling. So basically what I'm trying to do here is to find what plays the role of descending plane partitions that we saw in correspondence to alternating sign matrices, right?
May I ask a question about the previous?
Okay.
So what is the precise role of alternation in this generalized case? But in a sense, what precisely should be alternate in this matrix?
Okay. So it's both obvious and not easy to state. Okay. So it's obvious because we have these rules along horizontal, vertical, and diagonal lines. Okay. And so we know exactly what happens. Along each horizontal, you must have an odd number of reflections. Along each diagonal, you must have an even number if you're in type 3, or an odd number if you're in type 2 or 1. Okay, and that's it. Okay, so these conditions are just expressed as in the most simple way by these conditions. That's all. But translating them in terms of phases is kind of nasty, although you can prove some rules. For instance, it's kind of easy to show that the sum of all the elements of a certain type of matrices is given by something that you can compute, right? So there are some consequences that you can prove. But basically, in the end, we're going to be only interested in where the matrix is non-zero, right? And the limit shape will be the limit shape of a domain where the matrix entries are non-zero. Okay?
So, but why is it useful to write this omega and omega squared?
Just to visualize it as a matrix. And there is the hope, but I didn't want to discuss that, but there's also a connection between alternating sign matrices and cluster algebra. And I had the hope, and I still have the hope, that these objects are connectable to cluster algebra, but that's not done yet. And this formulation makes it kind of easier to visualize. Okay?
Thanks.
All right. So this other problem, which is a problem of domino tiling, and as I said, I was trying to emulate the descending plane partitions, which were domino rhombus tilings of some hexagon with a symmetry, right? With a hole in the middle and with symmetry. So here we have this. We have a quasi-Aztec square. So for those who know what the Aztec diamond looks like, this is almost the same, except that there are defects here, 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 and here. Okay. And moreover, because we impose those defects, there would be only an odd number of squares of a square lattice inside, which is no good if you want to tile it with dominoes, right? So you have to remove an odd number of squares. And so you remove this central cross right here, which is five squares are removed, right? And now it's tileable. And you demand in the same way as you did before that now it's rotationally invariant, but by 2 pi over 4 now, right? So this rotational symmetry.
One question
Yes.
about it. Is it true or a belief that a typical domino tiling of this domain without imposing this invariance will be almost rotationally invariant.
It's absolutely true. When the size is very large, first of all, this becomes a square, right? We don't see any details, right? The whole disappears completely, right? You have very, very large size. And of course, you expect the Arctic curve, let's say in a uniform weighting of dominoes, right? To have the symmetries of a domain, okay? And to be absolutely rotationally symmetric by 2π/4. Absolutely. And we'll come back to that, actually. Thank you for the question. Can I move on?
Thank you.
Thank you. So, okay, we want to count this. So we just determine the fundamental domain, right, which is 1/4 of the picture. And we look at the configurations of dominoes. And of course, everything I see here, I should see there, right? Because there is this rotational invariance, which basically means that we're looking at a cone with these two directions identified, okay? So the counting is very simple. Once you have realized that dominoes are actually in bijection with paths, and not just any paths, but Schroeder paths again, that is paths with vertical, horizontal, and diagonal steps, okay? So to see why, well, first of all, you have an underlying square lattice, right? So the square lattice is naturally bicolored, black and white, like a chessboard. Therefore, you might think there are only two types of tiles, right? The diagonal to the right and to the bottom, but in fact, there's four because they have to be bicolored accordingly, okay? So you have four types of tiles, and now you just decide to associate to them these configurations of the path. So the path goes top to bottom, left to right, and northwest to southeast, and it always starts in a black square and ends up in a white square. Therefore, of course, there's no way there can be a path on the last one, so it's empty. Okay, so here is a configuration just to show you how this works, right? So all these guys are empty because they're shifted. You see, this guy is shifted from this one by one, so the square and white and black squares are in different positions. So this one is unoccupied, but this one is occupied. Okay. So we are looking at a cone, right? So it's really like a nice cone with a hole in the bottom, right? And so that's very bad for ice cones, by the way, huh? Because you're going to dirty yourself. But or you have to eat very quickly. Anyway, so you have this cone that you want to tile, or if you want, you have to draw these non-intersecting Schroeder paths on the cone, right? And the point here is that all the points on the bottom where the paths end have to be at same positions as the points on the left where the paths start, with a little shift of positions because there's a hole, right? So the hole means there's a forbidden zone here in which the points can't be, all right? So this can be counted very easily. And here is the answer. The answer I put in a very economical form of the determinant of an n by n truncation, okay, of a matrix whose entries are generated by this series of z and w, right? So you take this rational fraction, you expand it in powers of z and w as a power series, right? And you extract the coefficient of zi wj, and this is my mij, okay? So clearly this is the generating function of the identity, right? Because it only has delta ij as matrix elements, because z and w must have the same power, right? So identity. And this is a certain matrix M, okay? And now Cauchy-Binet tells us that the determinant of identity plus a matrix is a sum over all minors, right? Diagonal minors of the matrix, okay? And now I just have to reinterpret the diagonal minors of this matrix here by using Gessel-Vienot. Gessel-Vienot tells me that I can, the matrix with given minors is actually the partition function for paths which start at the bottom points and end up at the top points. But here it's diagonal minors, meaning that the start and end points are the same. So on my picture, these I1, I2, Ik and I1, I2, Ik are just the rows and column labels that I have to extract to get the correct partition function for these particular configurations, the ones that start at these particular points and end up at those particular points. Okay, so the matrix elements count these partition functions, and now the minors are just counting for you the correct partition functions. All right, so this is very simple. So I just have to explain why this matrix here is given by this. So let's just concentrate on this piece of the denominator, which is the most important. Well, you see, to generate paths, you have to choose vertical, horizontal, or diagonal steps, right? So this is the generating function, which allows you to generate any choice of vertical, horizontal, or diagonal steps, right? So it's almost all in there. Now this just comes from the details of doing it correctly. Okay. Anyway, you compute now this thing very efficiently by just generating your matrix elements. And I find that the third one is 23. So it's determinant of identity plus this matrix here. And indeed, you can count them. There's 23 of those domino tilings of holy Aztec quasi-square, right? And I remind you that there were also 23 of those guys here in domain wall boundary condition 1. Okay. So the claim here is that this is actually a general fact, that the counting of configurations of my non-intersecting paths on the cone here is actually the same as the counting of configurations of a 20 vertex model. Okay, so how to prove that? Well, you have to compute the 20 vertex model configurations, and we do that first by using integrability. So we have to use integrable weights for the 20 vertex model. I'll show you how to find them. We'll deform the line arrangements from 20 vertex to 6 vertex, and then use 6 vertex results. So Isergin-Korepin again. And it's always boiling down to that. So it's really neat, and it's kind of minimal pain because you can really get quite quickly to the answers and even refinements. Okay, so let me show you how this works. So first of all, this triangular lattice is not nice because of these triple intersections at each vertex. Okay, so the idea here is to resolve the intersections into simple intersections by just moving down slightly every diagonal line. Okay, so you create now, instead of just one vertex, you trade it for 3 vertices, right, on 3 sublattices. Okay, but now on each of those 3 sublattices, you can use the 6 vertex model Boltzmann weights, which are going to ensure integrability of the system. So for the experts, we have now horizontal, diagonal, and vertical spectral parameters, or rapidities if you want, and the Boltzmann weights are going to be functions of all these. Okay, so just a fun remark here, this lattice here is called the Kagome lattice, okay? And it's not named after a Japanese physicist, but it's named after a Japanese method of weaving baskets. Kago means basket and me means a hole. Okay, so this is the basket weaving, the Japanese basket weaving, which gave rise to this name. Now here is another one, so it's also my background. So this picture, so I call it the lattice of Kagome. So Kagome is a delicious beverage that you can find in the good Japanese grocery stores. And I'll come back to this, okay? So just think of this as my lattice of Kagome. All right, so how do we do this? Well, once we have resolved the singularities, right, the intersections, then we have introduced these new triangles here, which were not there before. And so the black arrows stand for the configuration of a 20 vertex, right? And now we have to actually sum over all possible configurations of the blue arrows, which always exist. And there might be 1 or 2, actually. So this is how this works. But now, of course, on these 3 sublattices, I can choose 6 vertex model weights, which I do here. So you see I have sublattice 1, sublattice 2, sublattice 3. So 1 is with horizontal and vertical lines, and 2 is horizontal and diagonal, and 3 is vertical and diagonal. Okay. I have all these Boltzmann weights, which I can choose arbitrarily, basically, for the 3 sublattices. And now I will construct my 20 vertex weights by just summing over the configurations, right? So I take an arbitrary example here, right? So the weight of this vertex of the 20 vertex will be given by the product over all the weights of all the configurations, the sum over the configurations of product of the weights of the 3 sublattice 6 vertex models, right? So I have 3 weights. Here it's type A1, here it's type B2, and here it's type C3. And so you just look at these lines and you see the coding. And so, for instance, this W is just the sum of these products of 3 weights, okay? Now, the good thing about a resolution is that you want to be independent of the way you do it, right? So the other way would have been, instead of taking the diagonal down, to take it up, right? But then it gives rise to a completely different configuration. And this time there's only one possibility for the blue arrows, right? And it gives you B1, A2, C3. In other words, if I want to have an integrable solution in which I can move around the diagonals, I need a certain number of relations to be satisfied, right? And so I have to satisfy all these relations. And the solution will be what I call the integrable weights of a 20 vertex model. All right, so here it is. After a little bit of work, you see that there are 7 different weights that appear, and they are grouped actually according, there are groupings of the 20 vertex solution, 20 vertex environments according to this picture. Okay, so we have these 7 weights. Now I coded them using rapidities here. So eta is for the parameter q of a 6 vertex model. So we find out that the 3 6 vertex model must have the same value of q, so the same quantum parameter, but they can still have arbitrary rapidities. Okay, and so I code the rapidities in these ways. Of course, everything is projective, so this is fixed up to some global constant, and these are the weights. Okay, so now if I put those weights on my model, I can move around the diagonal lines freely. Okay, so I gain a lot of things here. Okay, a small remark here is that the uniform weights, that is all the W's equal to 1 for the 20 vertex model, right? So basically the uniform configurations will be a particular case. I just have to take my parameters to some very specific values, which actually correspond to these values of A, B, C in the 3 sublattices, right? So what's going to be important is actually the sublattice 1 between horizontal and vertical. And you see that it's not uniform. B is square root of 2. So to get the uniform counting in 20 vertex, you need to take non-uniform countings in the 6 vertex, which is kind of amusing. All right. Now, how do we connect our problem to 6 vertex? Well, we have all the elements. We start from a configuration, let's say in domain wall boundary condition 2, for instance, and we're going to move around the diagonal. So first I stretch the lines a little bit to have more space to work. And then I'm going to take all the diagonal lines above the diagonal, right? All the ones that end up with blue arrows, I will take them up. And then the rest I'll take down. Okay, so this gives me this. Okay, so now let's zoom in, say at this corner. You see, because of the choice of boundary condition, everybody was entering horizontally and coming out vertically. Okay, so it means that the 2 arrows here are incoming. Okay, but this is 6 vertex, so it's transmitted, right? Because 2 entering, 2 outgoing. So it actually propagates all along. And so in the end, I have entering arrows here. And all those configurations are kind of frozen, right? There's only one configuration, so it's one weight. So the partition function splits into a product of weights, which are very simple, times, so the same thing happens below here, times another product of weights, times another product of weights. And what's left is just the central part. And the central part, of course, is the 6 vertex model with domain wall boundary conditions on the sublattice 1. So a bunch of numbers times the sublattice 1 partition function, and the numbers conspire to get you 1, actually, so it's very simple. And so here is the theorem is that the partition function is counted by the 6 vertex partition function. And remember, on sublattice 1, it was not uniform. It was with 1 for A, but square root of 2 for B, and 1 for C-type weights. All right, so now let me zoom in on the picture that's behind me and see what it says on this delicious beverage called kagome. And it's made of 20 fruits and 6 vegetables, okay? So a colleague of mine to whom I sent this picture made me remark that there was this 20 and this 6, so the answer was there all along. All right. So here is the theorem, right, which I stated already. So you just put weight 1, square root of 2 and 1 to the 6 vertex, and that will count for you the 20 vertex configurations. Or if you want, you can view it in terms of the osculating path configurations. And whenever a path goes straight, it's a B, right? So when it goes straight, you pick up a square root of 2. So here you pick up 2 of them. So there's 2. Here there's a lot. There's 2, 4, 6. So 2 to the 6 over 2, which is 8. Okay, so you count now with weights 1, 2, 2, 2, 4, 4, 8, the 7 alternating sign matrices, and you find 23, which was my other number. Okay, so that settles it, right? So the partition function of a 20 vertex model with all weights equal to 1 is equal to that of a 6 vertex model with weights ABC, 1 square root of 2 and 1. So now we want to identify this result with the determinant I showed you before, right? So that's where Korekpin and Izergin come to the rescue with their beautiful determinant formula for the 6 vertex model with domain wall boundary condition. And so it's expressed in terms of the weights, in fact, the Boltzmann weights. So you just have to take a homogeneous limit of this. And at the end of a long day, in this limiting procedure, you will get a determinant. And you can actually show that this determinant is the same as the determinant I showed you before, and even with refinements. Okay, so that settles it. That proves this conjecture, which is now a theorem. Okay, so let me now go over the second type of boundary conditions, which is domain wall boundary conditions 3, where the numbers were this sequence. Okay. So if you put this sequence in the online integer sequence encyclopedia, you find that it actually gives you an answer which has to do with domino tilings again. But now it's of a 2n by 2n square, and it's actually not the bn directly, but 2 to the n times bn squared. Okay, so and that's basically in the list of things that Temperley and Fisher knew how to compute, right? Now, it took a long time until 97, 61, 97, to find actually an object which is enumerated by Bn. And it's really simple. It's just half of the square. But the half is taken in a very peculiar way, right? So you need a staircase with steps of length 2 to cut your square into 2 pieces. And now the number of domino tilings of this half is indeed given by, okay, a la Temperley Fisher, by a product of these eigenvalues of a discrete Laplace operator on the dual graph, but given also by these numbers. Okay. So conjecture, the configurations for domain wall boundary condition 3 are actually the domino tilings of Parter's triangle. Okay. But actually, there's more, you can say. You can actually extend these configurations I was looking at. Instead of looking at a square, you look at the pentagon, right? So now you're going to have, you're just pushing down your boundary condition from here and imposing empty boundaries here, right? So now you have two integers, n and k, right? K is the amount by which you've pushed down your configurations. And now you can look at configurations of this, right? So I call this a pentagon of triangular ice, right? Pentagon because there's five edges here. And at the same time, what you can do is start from the triangle of Parter and realize that when you describe it in terms of non-intersecting paths, again, it's domino tiling, so it's non-intersecting paths, just like I explained before. But the top here, the fact that there is this boundary right there means that the paths are constrained to not go too far up, right? So what you can do is relax a little bit this condition, or relax a bit more or more. So you see here, I come up with a sequence of numbers which are different, right? Bigger and bigger, and which correspond to having raised the roof above the Parter's triangle, okay? And this one I will call the Aztec triangle for some reasons. Well, it looks Aztec on the top, okay? And now the conjecture is bigger. It's that the enumeration of 20 vertex configurations with domain wall boundary free on the pentagons of ice, right, is actually the same number as the number of domino tilings of raised Parter triangles with a roof at same distance k as the k has been the displacement of the boundary on the bottom. Okay, so that's the conjecture. I have a proof of this conjecture in the extreme case of the rightmost guy here. So when you push the roof to infinity, so you remove the constraint of the roof. And here, if you push this to infinity, you end up with a quadrangle instead of a pentagon. And it's this picture, okay? So the number of configurations of domain wall boundary condition free on this domain here is the same as the number of domino tilings of this Aztec triangle right there. And that's my third sequence, 1, 4, 60, 3, 3, 2, 8. All right. So here is the theorem. The numbers are the same, but they are also enumerated by a relatively simple formula, which involves, again, just a rational generating function for a matrix, right, for matrix elements. And now you just truncate this matrix to its n first rows and columns and take the determinant, and that gives you the number. Okay, and because I had these numbers for arbitrary sizes, I was able to formulate a conjecture on what the number exactly is. And now look at this. This is remarkable because this looks very much like the formula for alternating sign matrices, except that there was a 3, which now is replaced by a 4, and the 1 on the bottom, which is replaced by a 2. Okay, and there's this extra term here. But apart from that, it's kind of a cousin of the other formula. Okay, and so all sorts of people have been excited by this formula. So far, nothing came out of it, but maybe something will come out. Just to show you that there's nothing really new here, it's just the same proof as before, right? Same weights, of course. So I can move around the lines, okay? So here I have to do a little bit of gymnastics, do it a little bit differently. But at the end of the day, once I have moved all my lines, I end up with yet another version of a 6-vertex model, which is called the U-turn boundary or reflecting boundary 6-vertex model, which was actually solved by Tsuchiya and also considered by Cooper-Berg. And again, it's a determinant a la Isergin-Korepin, but slightly different. Okay, so thanks to that, of course, you can use this fact and prove this theorem. Okay. So now in the remaining, I don't know, 7, 8 minutes, maybe, I'd like to discuss the limit shape problem. So now we have these configurations of paths, right? Osculating paths for the various models. And we can look at very large grids and very large and try to say something about typical configurations. So a typical configuration exhibits typically some frozen domains in the corners close to the boundary and liquid domains, that is disordered domains, closer to the center. Okay, so what does it mean? It means that frozen domain means that the paths are very regularly arranged, whereas liquid means they are disordered. So instead of continuing like this, let me show you actually a simulation. So that's size 200 for domain wall boundary condition 1, 20 vertex, okay, with uniform weights. So if you zoom in a little bit, so close to the boundaries, right, you have these paths which are extremely well organized, right? So this is one phase of crystal, right? This is another phase of crystal. Actually, this here, which is empty, is also another phase of crystal. This on the bottom is yet another phase. And here, another phase, and here, another phase. So total, I have 6 phases, crystalline phases, right? And then I have some domain which is completely disordered, right? Which I could call a liquid. And now look at this. There is a sort of a clear picture here, which comes out already at n equals 200 of an Arctic curve that is a sharper and sharper defined curve, which separates the frozen phases from the liquid phase. Okay, so to study this Arctic phenomenon, there is now a very nice method, which is called the tangent method, and which goes as follows. So in all cases, we are looking at a soup of paths whose ends are attached, right, on the left and on the bottom of the picture, okay? And when the size becomes very large, well, the shape of the outermost path is going to give you, at least in some of its parts, the shape of the Arctic curve, okay? So what we are going to do is detach the top path here and use it to tell us something about the other paths. So it's really like taking one of the prisoners and making him speak, right? So it's really that. And now the rest of the prisoners, they're not very much influenced by that. It's just one less prisoner, but there's a very large number of them. So they continue interacting in the same way, basically. And so this one is going to tell us something about exactly what the shape is when it's not there, okay? All right, so now more precisely, once I have taken my path to the new end, I have a configuration like this. So the path has to exit the domain, right, somewhere. And then it enters the domain and it ends up here. So at some point, it starts being part of a crowd again. Okay, and the idea is the following, is that asymptotically, when n becomes very large, there is still this Arctic curve, which is basically unperturbed, which doesn't care about a single path escaping, right? But now this single path becomes part of the Arctic curve again until the end here. So there's a point at which it reaches the Arctic curve and becomes part of it. And as when it's by itself, it has no influence of the other points. It takes the most likely trajectory. In the case of uniform weights, it's just a line. So this line is tangent to the Arctic curve, right? So this is the hypothesis. The hypothesis is that the line followed by the path that it has detached is actually tangent to the Arctic curve. So if for each z here, which is the displacement which I choose, right, I can find the most likely exit point from the domain, then I have to draw just a line between this point and the exit point, and this line will be tangent to the Arctic curve. Therefore, the envelope of all the lines parameterized by z is going to be the Arctic curve, or at least a portion of it. So that's the idea. So let me show you how concretely it works, right? So for 6 vertex, you have to consider this configuration. Okay, I rotated things around, but basically I took the path which ended up here and pushed its end far away to the right, okay, by some distance L, okay? So now I have the pink partition function and the blue partition function, right? And the sum of pink times blue over the position of the exit point here, all right? So what I want to find is the most likely exit point. So I want to find the largest contribution to the sum over the position here, right? And this largest contribution, of course, will be given by a saddle point approximation, which uses asymptotics of those two partition functions. So now 20 vertex domain wall boundary, one, same story, but now the paths are a little bit different. So I would say the blue side is easy because it's just a single path, right? With the weights of the 6 vertex or the 20 vertex, right? So the weights here are non-trivial, but still it's just a single path. So that's partition function that's very easy to compute. Now here, it's another story, right? Because it's a refinement of the partition functions we've seen before. But remember, in the Isargin-Korepin determinants, there are all these spectral parameters. And so actually, there's only need of one spectral parameter to get these objects. So we are in a very good situation. And here is the last problem I showed you. Again, same story. So they are all treated in the same way. So very briefly, let me just give you one formula for each. Okay. And so there are two things you want to compute. The first is the partition function. So it's because it's a determinant, it's a homogeneous limit of a determinant, it satisfies the so-called Denano-Jacobi relation, or if you want, Plücker relations, right? And out of those Plücker relations, it's not very hard to find a differential equation for the limiting partition function. And if you look at its asymptotics, you find a differential equation for the free energy, which is nothing but the two-dimensional Liouville to-die equation. Okay. Now, if you look at one-point function, so it's the objects that we wanted to compute there, right, with one refinement, which is one exit point somewhere, right? So these one-point functions, they also obey a very similar relations as a consequence also of Denano-Jacobi, but now, because there's one spectral parameter, which is different, you see, all the z's goes to u, all the w's go to v, except the last, which goes to a shifted v by xi, okay? So h is a function of xi, and we get this, this equation for it. And therefore, asymptotically, you expect this kind of leading behavior for h, and you find again a differential equation. So you just have to solve these two differential equations. I'm not doing it here, but it can be done, okay? And then
is xi is responsible for the exit point, is it?
Yes,
or?
exactly. Xi, you see, xi codes the last vertical spectral parameter, right? So if you look at this situation, the last spectral parameter is corresponding to the last line here. So it means that the weights, the Boltzmann weights in the last column are different because I shifted the spectral parameter. So I can use them to determine, right? I get a generating function for those objects by just having shifted the last spectral parameter. It's a bit technical, but I think you can.
Okay.
So, okay, so then we do the program I just said, right? You also have to compute the partition function for single path, do the saddle point, and you get an analytic formula for the Arctic curve. So this is this plot of the analytic formula on top of some colored version of this simulation. Okay. But now I showed you that I have a family of 7 different Boltzmann weights with 4 parameters, right? So I can play around and I can repeat exactly the same thing for all these families. So I get all sorts of interesting Arctic curves for all these differently weighted and biased, if you want, biased alternating phase matrices. So this would be like the shape of a very large APM, right? And these are shapes associated to a 20 vertex model with different Boltzmann weights. Now, we show the correspondence between this problem of wholly Aztec square domino tiling and 20 vertex, right? So I told you we can even refine the correspondence. And indeed, we can actually compute the one-point functions of the tiling model in terms of a one-point function of a 20 vertex. Therefore, we can also apply the same tangent method formula for the wholly Aztec square domino tiling. And as somebody remarked earlier, what you find is that the Arctic curve is this time algebraic, which is expected for domino tilings, but has this fourfold symmetry, which looks like a clover leaf. All right, so let me now just put everything on the same picture. So I have my coffee bean limit shape for APM here, right? And I notice the following thing is that the Arctic curve for the coffee bean is actually made of 6 pieces, and it's piecewise algebraic. That is, it's not algebraic. So you have to glue different pieces, this and this, for instance. They're not part of the same algebraic curve. But it's very close to being, because if you take the analytic continuation of this part, which is here, and apply a shear transformation, so you pull up, then you find this part. So in fact, it's piecewise algebraic, analytic, but in a very specific way, okay? Now, if I continue the analytic continuation, I get all this. And this picture here is actually the Arctic curve for the domino tiling problem with a little hole in the middle. So we're not able to show that there's a bijection between the objects, but asymptotically, what we find is that the Arctic curve is the same, at least in a certain portion, okay? So I think it's the next best thing to a bijection that we could find is that a certain statistic is the same in both models. Just to show you that this is not a new phenomenon, it actually appeared already in the alternating sign matrices descending plane partition. So people have computed the limit shape of alternating sign matrices. Now it's proven by Agarwal. And it's made of 4 pieces of ellipse which are glued together, okay? So again, it's only piecewise analytic. But if you take the analytic continuation of this piece, it gives you a large ellipse, which is actually the limit shape for the DPP, descending plane partitions, rhombus tilings of the hexagon, which you put in the same lattice. So finally, my other problem also has an Arctic curve. Now, of course, the problem is that nobody had computed the Arctic curve corresponding to 6 vertex with reflecting boundaries. So there was more work, but it could be done. And again, if you analytically continue this portion of Arctic curve, you find that it has this fourfold symmetry, which is more surprising because this other problem didn't really have a fourfold symmetry, right? And if you put together the result for the domino tiling of the Aztec triangle and the quadrangle domain wall boundary condition free 20 vertex, you again find that the 2 problems have a portion of Arctic curve which is the same. Now the analytic continuation here corresponds to this model. And here, this is again a shear of the analytic continuation of this part. Okay, so there's a very, very interesting interplay between Arctic curve in these problems, which are not really in bijection, or at least they are in bijection. We know it's the same number, but for which we have no natural bijection. Okay. All right, so I want to conclude now, a bit over time. So I hope I convinced you that triangular ice does have interesting combinatorics of osculating lattice paths. These alternating phase matrices, I still don't know yet whether they're going to be useful or not, but maybe they will. One can look at, class of symmetries of those APMs, just like people have looked at classes of symmetries of alternating sign matrices. That seems to be interesting too. And then there's this Arctic phenomenon, which works for all the cases, right? Domain wall 1, 2, domain wall 3, okay? And in each case, it's really because there's a connection to 6 vertex or U-turn 6 vertex, right? Reflecting boundary 6 vertex. And finally, there is this intriguing phenomenon of non-analyticity, but also of shear phenomenon of the Arctic curves, right? And so this is really the case for interacting fermions as opposed to free fermions. You see, everything that's a tiling uses non-intersecting paths that don't talk to each other, right? I mean, only by the fact that they are not intersecting each other, right? But in the sixth vertex, we do something else. We allow paths to come close together, right? And we put a different weights when they come close together. And so typically, instead of having free fermions, we go over to interacting fermions. And so this phenomenon of non-analyticity seems to be on a par with the fact that the fermions interact in a certain very specific way, right? These osculating points. So I think this has to be better understood. And spasiba.
Спасибо, Philippe. Okay. Other questions?
Yeah.
I have one. Okay. Philippe, there was an interplay with 6 vertex model putting on triangle. Is something known about playing with the 8th vertex model?
No. So you see here, I was really insisting on the combinatorics, combinatorial content, which really has to do with the influence of the boundary condition on the model inside, okay? And so the ice rule is crucial, I think, here. The ice rule is really transmitting the constraint of the boundary condition inside the domain. And it's what creates this Arctic curve. That's what creates all the physics in there, right? Now, if you look at the 8 vertex model, you lose that because you're allowing sources and sinks, okay, which can proliferate, and it sort of destroys this very strict and constrained structure, right? So I'm not saying it's not interesting. It's actually some people have started looking at some combinatorics inside the 8 vertex model. But what I'm saying is that it's probably of a different nature.
Okay, thank you.
I have a couple of questions. First of all, Philippe, what do you mean by integrability in this problem?
All right. So I'm really using, you see, maybe I didn't explain in detail, but I'm using the integrable weights of the 6 vertex model, right? So basically those that come from the trigonometric R matrix, all right? And I use those guys, and I make sure that when I resolve my singularities, my triple intersections, the way I do this resolution is independent. I mean, the result of a resolution is independent of the way I do it, which means an extra condition. There are some extra conditions on top of those this basic choice of integrable weights of the 6 vertex model. And I believe that makes the 20 vertex model integrable in maybe not the sense that you would have hoped, but at least one in which you see this freedom of moving the diagonal lines, right? Because of this Young-Baxter equation that I enforced is actually crucial to solve the models, right? Now, I'm not saying I'm capable of using beta ansatz and all that technology, but I don't need it, in fact, right? I just need to use smartly enough the results of Isergin-Korepin, in this case, to solve the model.
And one more question, you have mentioned some connection, certain connection with cluster algebra structure.
Yes.
Can you give more detail?
Okay, so an alternating sign matrix, right, which is a collection of zeros and ones and minus ones, right, is actually a coding for monomials. Okay, so imagine that you have a monomial which is a product of aij, right? And now the power you're going to put at aij is the entry of a corresponding alternating sign matrix ij. Okay, so let's call maybe no, not a, let's call them xij. right? So I have, maybe I can use, yeah. So I'm going to, so from the alternating sign matrix, I'm going to give you a monomial, right? So I'm going to do product of xij to the aij, right? So here it's aij. So you can associate a monomial, all right? So what happens is that there's some specific cluster algebra, which is called the T-system cluster algebra, which corresponds to a quiver, an infinite quiver.
Sorry, Philip, and this is before you introduce the square roots of unity, yeah?
Yes, yes, yes. This was in the other case. I'm first reviewing the alternating sign matrices and their connection to cluster algebra, okay? And so the way it works is that if you consider the cluster algebra with this quiver, right, etc., and you look at the evolution, right, obtained by mutating at every other point, and then mutating at every other point. Okay, so this is the kind of evolution you're looking at in your cluster algebra. So it involves an infinite number of mutations. Okay, now if you do this repeatedly, right, you're going to produce, in fact, new cluster variables, which are sum of monomials, right? And the monomials will be expressed in terms of the initial seed of your cluster algebra as sums of your alternating sign matrices of these type of monomials with coefficients, okay? So fundamentally, the alternating sign matrices have to do with this cluster algebra, okay? So here my dream is that maybe there is another cluster algebra that one come up with, right, for which these APMs are going to play a similar role. And you see, what you want is a collection of powers of variables that you're going to put in a monomial, right? And so I showed you that there was a formulation as triples of zeros, ones, and minus ones. For instance, you could imagine that you have a triple of variables and that you're looking at monomials of those guys. And so I know the problem is not well posed, but I have a feeling that maybe there's a cluster algebra hidden behind this.
I see. Thanks.
But when you were answering Pasha's question about these roots, it seems to me that you said that it somehow clarifies the relation to cluster algebra, isn't it?
No, look, it's completely bijective, okay? A triple of integer 0, 1, minus 1, or
so this 0 plus 1 minus 1 simply means that your quiver has only single arrows, yeah?
No. You see, it's a triple. So it means that it's a tensor now, right? It's not an alternating sign matrix. It's an alternating sign tensor.
I see.
Yeah. Okay. So it's.
So you were considering tiling of a square with a hole inside, right?
Yes.
But the hole, but then you take your box big, but the hole stays finite, right?
No. The hole disappears. No.
Yeah. This disappears because you look from afar. That's why it disappears.
Yes, absolutely. But it's there in the definition, and it has to be there. Yes.
Right. But can you do a case when the hole grows, has the same order of size as the?
Good question. I think it's very easy to do. I didn't do it because I didn't have anything to connect it to, right? Mm-hmm. But definitely it's easy to do, right? It just means that you see here in the enumeration. Let me find the page again. Where is it? Okay, it's far away. Here, right? So in the enumeration here, the presence of this cross here, this hole in the middle, just meant that when I looked at my problem, I had only a small portion that was forbidden here, right? Now, if you take a bigger cross, you're going to just forbid a larger domain here, right? So it's not going to change fundamentally the calculation. So my guess is that instead of having just first n rows and columns, maybe it will be a window inside this infinite matrix, which is not connected to the top, but maybe a bit further in, you see. So I don't think it's a difficult object to compute. The question is what to do with it, right? And what to connect it to.
May I also ask a couple of questions? So first, is there some algebraic structure behind this ICE model, something like quantum groups or whatever?
Well, you see, I think the algebraic structure is the same as the 6 vertex, right? It's just a way of using. Okay, now you could ask, but how does this structure manifest itself, right? So in a sense, I've used as much as I could this connection to 6 vertex to be able to say something about this, right? But certainly I haven't looked at the algebraic aspect, and I think there is something there that still has to be done. Yeah. So good question.
Thank you. And also one more question: is there something like 8 choose 4 model?
That's a good question too, but the answer is no, and for a reason that so you could think of bathroom tiling kind of object, right? So you see, you need to have straight lines. Let me just go to the end and add up one page. So I think what you have in mind is something like this, right? So you would have a square lattice, and then instead of putting just one diagonal like this, you put 2 diagonals.
Well, for example, yeah.
Right. So now you see, here is the problem. You have 2 types of intersections, right? You have simple intersections and these 8-fold intersections. So you could think, of course, of resolving these ones, right, by using an analogous thing. But then the problem is that when you start trying to move your diagonal lines, you're going to run into inconsistencies between those 2 types of vertices. Okay, you have to sit down and do it. But I think that's where it stops. That's where you can't go on. So the answer is no. I think no.
So you're saying that if you want to draw it on a plane, then there is no way, right?
Yes. So then you would have perhaps to really think that these 2 lines don't cross. Right? So go over to some higher surface or something. Okay, that may be, but I haven't tried. Yes.
Thank you.
Welcome.
May I ask a question?
Sure.
You mentioned that your partition function was a determinant which some kind of generating function, and then it was a sum of Gesell-Vinot determinants.
Yes.
Does it mean it has something to do with a free fermionic point?
Yes, yes, absolutely. So let me go back. This was a tiling problem, right? And we know that all the tiling problems are free fermion problems, right? One way to see it is that you can rephrase it in terms of lattice fermions, right? The Gesell-Vinot theorem, after all, is just the weak theorem for lattice fermions, right? But these people didn't know what a fermion was, so it's okay. But so yes, the answer is yes, indeed.
Because usually these alternating sign matrices, they are associated to this cubic root of unity, and it's not free fermionic, right?
No, it is not. And my point here is that, let me go back to my value of Q as well. Where is it? My value of Q for the 20 vertex model is actually e to the I pi over 8. So it's definitely not free fermion either, okay? So here is the thing, that you have the coincidence of a number of configurations in a free fermion model and in an interacting fermion model, right? These 2 numbers are the same, but one sort of has undone the interaction of the other, right? So this is what's so interesting and intriguing about these correspondences, right? And that already existed between alternating sign matrices, which you can think of as interacting fermions, like you said, and descending plane partitions, which were just free fermions, right? And the Arctic curve somehow knows about this, right? Because there's a portion of Arctic curve which is common to the two problems. But the analytic continuation gives you the correct answer for the free fermion, but doesn't give you the correct answer for the interacting fermion. What you have to do is apply a shear on top of it.
Okay, thank you.
Welcome.
More questions?
So I wanted to ask, there was some formula for Laplace eigenvalues on a triangle. So could you explain how to compute them?
Triangle. So the last, you refer to the last problem. Let me try to find where it is. Here, this thing?
Yes.
Okay, so you're asking how do I count the configurations here? Well, you see it's non-intersecting paths.
I'm asking about the formula for Laplace eigenvalues, where you have a sum of squares of sines or sines. I don't remember.
No, okay. So we're talking about a different formula. Sorry, I misunderstood you. Where is it? Here. Okay. So you mean this formula?
Yes.
Okay. So where does it come from? But it really comes from Temperley-Fisher. It's just one of those dimer models, right? So you have a very efficient way of computing partition functions for dimer models by use of a Castelline matrix, if you want. But in fact, it really boils down to diagonalizing the discrete Laplace operator on the graph, right? The underlying graph. So here you have an underlying graph, which looks like a triangle of square lattice, right? Something like this. And so, okay, it's bipartite, so you have to be careful with the black and white vertices. There are small differences, but in the end, computing this number of domino tilings is the same as computing the number of dimer configurations on this graph, which itself is just a regularized version of a determinant of a Laplace operator. So you have to just remove the zero modes, okay? And these are the eigenvalues. So the product of eigenvalues gives you the determinant, okay? Now, between this formula and an actual integer, it's non-trivial, right? Even the machine has difficulties, right? If you give this to the machine and ask, okay, what integers are coming out, it will very quickly be quite hard for this machine. So this is definitely not the formula I wanted, okay? But there are other ways, right? And one way to compute this is by using non-intersecting paths again. So you use Gessel-Vienot, all right? But it's also tricky because there's a roof, right? So the roof means the paths are constrained. And so whatever you put in your matrix is already non-trivial, okay? And then you take a determinant. So basically those numbers you can compute, right? You have this formula, but it's kind of numerically even, it's not so easy to get them, right? And so far it's just a conjecture, right? This are just conjectures, but this one I showed you can be computed in a different way, which now is settled, okay?
So maybe it's not obvious how to diagonalize this matrix on a triangular graph because we don't have Fourier transformation there, but maybe I can learn it.
I'm not sure I didn't really understand. The sound is pretty bad. So did anybody?
No, Pasha, can you go to microphone closer?
Yeah, so I asked how to diagonalize this Castellan operator on the triangular graph because it seems that we don't have Fourier transformation and so on. But maybe it's better to read the corresponding papers.
Probably. I don't.
More questions? Then just thanks, Philippe.
Well, there is at least one question about that Aztec diamond with a hole. And Philippe, you mentioned in your paper on this that basically there is one parameter of each domino tiling which just the height of that hole, and in your computation you just do not care about this height of the hole, right? But
no, wait. What do you mean by height of the hole? I don't get it.
One can assign to each domino configuration so-called a height function.
Sure.
And there will be a particular hole related to the boundary of particular height of the hole, which is just increment along the bottom line.
Okay, so maybe what you mean is the number of lines then.
Yes.
Okay, all right, yes. So if we look at this configuration, for instance, there's a configuration with 0 line, certain number of configurations with 1 line up to here, and then the rest with 2 lines. Okay, so that would, yeah, okay, so you would say this is height 2 for the whole, then this is height 1, this is height 0, I guess, also, or maybe the opposite. Is this what you mean?
Yes, well, basically, I mean, a question about how to, is it possible to extract from the formula the number of domino tilings with the given number of lines?
Yes, it's very easy. You see, the number of lines is the number of matrix elements here, right? The number of choices of lines or columns, right? So if you put a t here, right, it's going to be t to the power number of lines. Okay, so just put a t here, and then you get your function. Okay.
Thank you.
Okay, thank you.
Thank you.
Bye.
Nice seeing you all. Bye-bye. And I'll see you next year, I guess. Huh?
Yeah. Thank you. Goodbye.
Thank you. Bye.
Okay, thank you.
Bye.
Bye.